Okay, so here we go on our first practice problem. Okay, so our first one reads, the yellow light given off by sodium vapor lamps is used for public lighting and has a wavelength of 589 nanometers. What is the frequency of this radiation? So, when we're trying to figure out frequency, we're talking about a wave. We know that much. And we see, okay, it's yellow light, so it's visible light. We can see the light. So our visible light formula is C, speed of light, equals lambda V, or frequency. Okay, we know that C equals 3.0 times 10 to the 8 meters per second. We also know that the wavelength is 5.89 nanometers. So my lambda is 589 nanometers. Okay, the kicker is, though, in wavelength, we want to get it to meters. So what we're going to have to do is write out what we do know, which we've done. We write out the speed of light and what's given, the 589 nanometers. Now we're going to have to rearrange our equation or use our wave triangle. In this case, I'm going to use the wave triangle. So we have our wave triangle, C, lambda, and V. And let's see if I can draw this out good enough. Okay, so we're looking at our triangle, and we are trying to find frequency, which is V, so we're going to cover up frequency. Okay, that gives us C, speed of light, over wavelength. Well, so now we have our formula. That's good. We have frequency equals C divided by wavelength. Now we got to get everything into appropriate units. So I'm going to make myself a little section here and get my 589 nanometers to meters. So I put 589 nanometers over 1. Okay. Then I'm going to convert that to meters. So meters, nanometers. 1 meter is 10 to the 9th nanometers. Okay? Once I multiply all that out and divide, so I multiply my tops, multiply my bottoms, and then I divide my top by my bottom, I get 5.89 times 10 to the negative 7th meters. So now I have my wavelength. I have my speed of light. All I do now is take my speed of light, 3.0 times 10 to the 8, divide by my wavelength, which is 5.89 times 10 to the negative 7th, and I get my frequency. I'm going to have to erase some of this over here, so here we go. And I get my frequency, which is 5.093 times 10 to the 14th hertz. And that would be my frequency. So what we did here, wrote down what we knew, then we figured out a formula for what we were trying to solve for, and then we converted everything to proper units and then plugged into our formula. Okay, so that's question 1. Question 2. A microwave oven emits a microwave energy with a wavelength of 12.9 centimeters. What is the energy of exactly 1 photon of radiation? Okay, so this is dealing with our photons. So we know our photon equation is E photon equals HV. where we know h is Planck's constant, which is 6.626 times 10 to the negative 34th. Yes. And we don't know V or obviously E. So how the crud are we going to solve this? Well, we're going to have to solve for V before we could solve for E. So we're going to have to do a separate equation here in which we know how to solve for V. Well, in our visible light equation, we have C equals lambda V, where C is speed of light, 3.0 times 10 to the 8th. And we know lambda is wavelength, which we have here, so 12.9 centimeters. We want to convert that to meters, and we're solving for V. Okay, we go back, and just like we did on our last one, we know our equation is for solving for V or solving for frequency is speed of light divided by lambda equals frequency. Okay, so we just need to be able to convert our wavelength to meters before we do this calculation. So if I take my 12.9 centimeters, put it over 1, multiply it by, there's 100 centimeters in 1 meter. That's going to give me, let me see, 0.129 meters. Okay, so that's going to be my lambda. So I'm going to take that now over here and do my speed of light, which is 3.0 times 10 to the 8th divided by 0.129, and that's going to give me my frequency of 2.33 times 10 to the 9th hertz. Okay, so that's going to be my V. So that's going over here. Okay, so I'm going to write that out. I'm going to erase some stuff so now we can go back to our E photon equation. Now that we solved for frequency, we have frequency in here. So 2.33 times 10 to the 9th hertz. So now that I have frequency and Planck's constant, I can solve for my energy of photon. All I do is multiply H times V, and that's going to give me 6.626 times 10 to the negative 34th times 2.33 times 10 to the 9th, and that gives me a total energy of 2.844 times 10 to the negative 43rd joule seconds. Okay, and you think about this, this is a really small number. Why does this make sense? Because we're talking about 1 microportion of an atom, a photon. So this isn't even a full atom, the energy a full atom can make. So it's going to be a small amount. So to reiterate where we went on this, we realized after writing out our equation of E photon equals HV that we did not have our frequency of the wave. So we had to solve for frequency using our visible light equation, which is C equals lambda V. We were given our wavelength, so we used that and our knowledge of what C is, the speed of light, and we were able to solve for frequency. Once we had our frequency, then we could plug it into our E photon equation and solve for it. Okay, that's about as hard as you're going to get on these types of questions, so let's work on to number 3. A certain electromagnetic wave has a wavelength of 625 nanometers. What's the frequency of the wave? Okay, so for this one, we are going to use our visible wavelength, or for this one, we're going to use our visible wave formula again. So C equals lambda V, where C equals 3.0 times 10 to the 8 meters per second, and we know lambda is 625 nanometers. We need to get that to meters, and we do not know our frequency. We're solving for that. Okay, if I put up my triangle again, C lambda V, let's see if I can draw this out. No, I'm so great at this. We're wanting to solve for frequency, which is V, so if we squiggle that out, cover that up, we have C over lambda. So this is our equation is going to be speed of light over wavelength equals frequency, but our kicker is we got to get our wavelength into meters. So our first step is going to be taking our 625 nanometers and converting it to meters. Okay, so we get a wavelength of 6.25 times 10 to the negative 7th meters. Okay, now we can plug that in over here. So we have 3.0 times 10 to the 8th divided by 6.25 times 10 to the negative 7th. Once I divide them out, I get 4.8 times 10 to the 14th hertz. And that would be my frequency. Okay, number 4. A laser emits a light with a frequency of 4.74 times 10 to the 14th hertz. What is the wavelength? So we continue with our visible light equation. C equals lambda V. Well, we see we're given frequency this time, and we're wanting wavelength. So we have in this equation, C is our speed of light, 3.0 times 10 to the 8th meters per second. We don't know our wavelength, that's what we're solving for, but we do know our frequency this time, which is 4.74 times 10 to the 14th hertz. Okay, this is an appropriate unit. This is in appropriate units, so we don't have to worry about anything further. All we have to do now is solve for wavelength. If we draw a triangle out, C, lambda, and V, and we cover up our wavelength, that's going to give us C over V, or speed of light divided by frequency. So we take our speed of light, 3.0 times 10 to the 8th, divided by our frequency, which is 4.74 times 10 to the 14th, and that's going to give us a wavelength of 6.33 times 10 to the negative 7th, and wavelength is in meters. Okay, so that one's not too bad. That one was pretty straightforward. Okay, so now let's work the fifth one. This is our final one. What is the energy of a 7.6 times 10 to the 14th hertz wave? So, same situation as our last one, except for now we're asking for energy. The energy equation is E equals HV. Okay, we know H is Planck's constant, which is 6.626 times 10 to the negative 34. We know the frequency is 7.6 times 10 to the 14th hertz. So V equals 7.6 times 10 to the 14th. Okay, we're trying to find E, so there's no need to rearrange this equation. So we just take 6.626 times 10 to the negative 34, multiply that by 7.6 times 10 to the 14th, and we get 5.076 times 10 to the negative 19th. And that would be the amount of energy, joules seconds, would be the amount of energy we get from this. Okay, I hope these kind of showed you how to work some of these. A lot of them are just going to require some fiddling around with it. Remember, your units need to be converted to proper units. So make sure wavelength, lambda, is always in meters. If it's not in meters, you need to convert it. Okay, frequency is in hertz. You won't ever have to worry about that because that's too advanced for y'all at this point. Okay, energy is joule seconds, and speed of light is meters per second. Okay, so make sure you know those and you're able to convert to those. Remember to use your wavelength, or make sure you're able to use your wave triangle, whether that is for the energy of a photon, energy of a wave given off, or even for your speed of light equation like we did multiple times here. And saying, I hope this kind of helped you out again. If you have questions, you can always ask me. Good luck and keep up the good work in class.